atomic structure. This is actually going to be part 1 of 2 in a video sequence. I just wanted to split these 2 videos up, so if you need more work on atomic structure, you have one video to watch. If you need help with periodic trends and not atomic structure, then you have the other video to watch. And if you need help with both, then you can watch both. But basically, I just wanted to make this easy for everybody. Every time. Okay, so lesson objectives, what you'll be tested on for the quiz coming up this week. 1, describe the structure of an atom given its atomic number, mass number, and charge. In video 2, we'll go back and redefine electronegativity, ionization energy, and atomic radius. And we will compare the electronegativity, ionization energy, and atomic radius of elements based on their position on the periodic table. So let's just do some atomic structure review. First things first, an atom is a basic building block of all matter. Matter cannot be broken down into substances smaller than an atom while maintaining properties of its element. So for all of you out there that are like, hey, there's protons, electrons, neutrons, even quarks. Yes, these are bits of matter that are smaller than atoms, but those pieces of matter do not maintain any properties of the element, which is what we're really interested in. Atoms are made of 3 subatomic particles: protons, neutrons, and electrons. Protons are positively charged. They have a mass of 1 AMU, which is atomic mass units, and protons live in the nucleus of an atom. This center bit here, that's our nucleus. Neutrons are neutrally charged, meaning they have no charge. They also have a mass of 1 atomic mass unit, and they also live in the nucleus. So you'll see here this little red plus sign is our proton, and this green circle with no charge in there is our neutron, both of these making up our nucleus. Last but not least, we have electrons. Electrons are negatively charged. Their mass is negligible, meaning we don't really count that into the atomic mass number because they're so small that we just don't care. They do have a mass, but it's so tiny. Electrons live in the orbitals outside of the nucleus. This is a Bohr's model of an atom, helium in this case. Electrons actually don't orbit like planets do around the sun, but this helps just to visualize kind of what's going on. As you saw in previous videos, electrons are actually around the nucleus in kind of a cloud, and the shape of that cloud that they can possibly be in depends on the orbital that the electron is in. Moving forward, describing atomic structure. So how do we do that? First, we need to know the atomic number. The atomic number is equal to the number of protons, and this determines the type of element we're dealing with. So when you look on the periodic table, it's ordered. You have 1 is hydrogen, 2 is helium, 3 is lithium, 4 is beryllium, 5 is boron, and so on. That number I just listed for each one of those is the atomic number. It's always going to be equal to the number of protons. So if I have an element that has 17 protons, I know it's chlorine. Just by definition, it has to be chlorine. The next number we deal with is the mass number. It's equal to the number of neutrons plus the number of protons. And this is always a whole number. We are never going to have an atom that has half a proton or half a neutron. Nothing like that. They're going to be whole numbers. You might be thinking to yourself, okay, but on the periodic table, there's decimals beneath the atomic symbol, which is our mass. The reason that we see decimals there is because the number reported on the periodic table is actually an average of all isotopes of that element. So if you look at, let's just keep it simple. Let's say hydrogen. Hydrogen has an average atomic mass of 1.0008, I think. The table's a little far away. That doesn't mean that we have a hydrogen atom that has that odd mass. It just means that most of our hydrogen atoms have an atomic mass number of 1, and every once in a while we'll have a hydrogen that has an atomic mass number of 2, meaning that it has 1 proton and 1 neutron. The neutrons can change, the protons cannot. As soon as we change the protons, we have changed the element. That's important to note. Last but not least, we have the charge. The charge of the ion will be reported in a little plus or minus with a number to the top right of our atomic symbol. You'll see what I'm talking about in a moment. I have two examples here. These are two different ways to represent an atom, okay? The first one, I have copper 63. This is one way to write, okay, what are we dealing with? We have the element name, and we have this random number sitting to the right of it. This number is our mass number. This copper in particular has a mass number of 63. And I want to know, when I ask you to describe the atomic structure, I want you to tell me how many protons, neutrons, and electrons are in that atom or ion. And let me back up a bit. An ion is just a charged atom. I don't think I said that. Okay, we're back. So I'm going to look for copper on the periodic table. It is number 29. 29 is the atomic number. It is also the number of protons. So I have 29 protons. To find neutrons, I'm going to have to do a little bit of math. I know that the mass number, which is protons plus neutrons, is 63. So I can take away the protons and I'll be left with neutrons. And 63 minus 29 happens to be 34. I must have 34 neutrons. Last but not least, electrons. This is where the charge comes into play. There's no charge listed here, so I can assume this copper atom is neutral, meaning it has no charge. For any neutral atom, the positively charged subatomic particles and the negatively charged subatomic particles must equal each other to cancel each other out. In this case, I have 29 protons. To neutralize that, I will need 29 electrons. And that's what we get. 29 protons, 34 neutrons, 29 electrons. If you want to double check your work, your protons and neutrons should add up to the mass number. And if we have no charge, your protons and electrons should be the same. And your protons always need to be the same as the atomic number, which is on the periodic table. Now let's try the second example. I have sodium, and then I have some numbers around it, and you see a little plus sign. So let's talk about what these mean. This is just another way to represent an atom that we're talking about. In this case, it's an ion. The number on the bottom left is our atomic number. It's a little bit confusing because the atomic number on the periodic table is actually on the top. I don't know why they change it. That's just how it is. You can also remember that one of these numbers is just protons and one of these numbers is protons plus neutrons. The smaller one has to be the just protons number. You can also double check just with the symbol in the periodic table. I have Na, which is sodium. Sodium on the periodic table has an atomic number of 11. This is my atomic number. This is my number of protons. Then to get neutrons, we subtract our mass number, which is 23. That's what this guy is, mass number. Minus our protons gives me 22 neutrons. And then last but not least, this plus sign tells me the charge. When you see a charge and there's no number next to it, assume it's a 1. Chemists have this whole thing against the number 1. We just don't want to write it down if we don't have to. If you see a plus sign, it's just plus 1. We have 11 protons, and we can't change that, so we're going to have to change the electrons to make this a positively charged ion. I'm going to have 10 electrons in this case. 10 electrons and 11 protons will leave me with a +1 charge overall, where the protons are winning out. And that's why we get this charge. So boom, 11 protons, 12 neutrons, 10 electrons. Again, you can always double check your work by saying, okay, does this add up to my mass number? Is this my atomic number? And do these two together give me my +1 charge? Moving forward, more on atomic structure. We're still looking at a sodium ion like in the last example. We're going to compare it to just a sodium atom. It has no charge, so you'll see it has 11 protons and 11 electrons. They're balanced and there's no charge. I'm actually going to try to draw it here, which will be a little bit tragic, but it'll be okay. I really need like a little mouse. I'm just working on a laptop, but it's fine. When you draw an atom, which I'm not going to ask you to do often just because I'm just not, I don't feel like it this semester. I'm going to see how that goes. The nucleus is going to have our protons. Oh gosh, that's so ugly. That's okay. I have 11 protons in the nucleus, and I have 12 neutrons. The P plus just equals proton. That's like my little shorthand. 12 neutrons. That's supposed to be a 0 there. Means no charge. There in the nucleus. Okay, then our electrons are going to fill out in a particular way that has to do with the shells and the orbitals that can be in that shell. You'll remember in the last video from last week, we go 1s2, then 2s2, 2p6, and so on. That 1s is our first shell. So let's draw this first shell. Our first shell only has the s orbital, which can hold 2 electrons. 1 electron there, 1 electron there. That's 2. I'm going to put 11. Let's draw our next shell. Our next shell is shell number 2. Our second shell is different because we can have the 2s orbital and the 2p orbital. The 2s orbital can hold 2 electrons, and the 2p orbitals, there's 3 of them, can hold 6. So we have a total of 8 electrons we can put in the second shell. I'm going to go ahead and put all 8. 1, 2, 3, 4, 5, 6, 7, 8. You guys should really start like a GoFundMe so I can get a cute little Surface Pro, and then your pictures will be better. Say it's for your education. Anyways, I have 8 electrons in my second orbital, and then I have 2 in my first orbital. I'm up to 10. We need 11, so we have to go to our third orbital, our 3s orbital. Excuse me, our third orbital. Oh my gosh, let me try again. Third shell, 3s orbital. We go up to 3s1 for sodium. 3s1. So that's our 1 lonely electron. We have up to 11. I super would never ask you to draw an atom larger than this because our third shell gets weird with that d orbital. The rules change. I just don't want to deal with it, and neither do you. So yeah, that's what our sodium atom looks like when it's neutral. A quicker way to show this is to go Na, which is our atomic symbol, and then just do 1 dot. What that 1 dot tells me is we have 1 valence electron. This is our valence electron. A valence electron is just any electron that exists on the outermost shell of the atom. Valence electron. This is called a Lewis dot diagram of our atom. Okay? Okay, let's do this one as well. And then I promise I'll never make you sit through this again. Again, in our sodium ion, we have 11 protons still. It's still sodium. Protons don't even change. I still have 12 neutrons in this case. If we had a different isotope, we could have maybe 11 neutrons. We're just going to keep it the same. That's my nucleus. And then I want to distribute 10 electrons. So again, we're going to start with our first shell, which only has a 1s orbital. It can hold 2 electrons. Then we're going to move on to our second shell. It has the 2s orbital and 2p orbital. It can hold 8 electrons. And I'm done. That's 10. That's 10 electrons right there. And then you'll notice again, we have 11 protons, 10 electrons. Protons win. We're left over with a positive charge. And there's our Lewis dot diagram. So it looks really sad. That's okay, you get the point. In this case, we have 8 electrons. So we have 8 dots around our atomic symbol. And boom, that's our Lewis dot diagram for sodium ion. You'll notice here we have 8, which makes this ion way happier. Atoms are most stable. Oh, okay. Atoms are most stable with 8 electrons in their valence shell, or 8 valence electrons. So this one is way more happier than just our sodium atom. Oh my gosh. Oh my gosh. Yeah, okay, you get the point. Last thing, I already defined this, but a valence electron is an electron in the outermost shell of an atom. This is our last little bit of information, just other terms to know. I've mentioned them, but didn't explicitly define them. An isotope is 2 atoms of the same element with different mass numbers. So they have a different amount of neutrons, same amount of protons. An ion is a positively or negatively charged atom. And there's 2 types of ions. We have a cation, which is a positively charged atom. I remember the T looks like a plus sign and is positive. These ones have lost electrons. So like our sodium example we just finished. An anion is a negatively charged ion, and it has gained electrons. So if you gain something negative, you're more negative. If you lose something negative, you're more positive. We have the octet rule. This states that atoms are most stable when they have 8 valence electrons. And yes, there are exceptions. We won't really discuss those right now. Maybe later, we'll see. If you want more practice before the quiz, you can find some really great examples on page 129 in your textbook, questions 66 through 75. And hint, hint, they might look a whole lot like your quiz. Next video will be about periodic trends. No, I don't want to keep that. Anyways, I will see y'all next time.